Hello everyone. In this video, I will introduce our work, a bytecode-based approach for smart contract classification. The motivation is there are millions of smart contracts. How to classify and label them? Currently, the classification of smart contracts relies on manual labeling, which is costly and inefficient. Another solution is using natural language processing techniques to classify the smart contracts based on their source code. Actually, some NLP-based classifiers have been already proposed. However, NLP-based models have limited application scenarios because they can only classify open source contracts. But open source code is not compulsory for smart contract developers. According to our literature review, less than 4% contracts are open source on Ethereum, which means that NLP models cannot classify more than 96% of smart contracts. So the question to answer is, how to classify smart contracts without source codes? I was inspired by the wide use of operation code features in other areas of smart contracts, such as contract vulnerability detection and fraud detection. We found that opcodes can reflect the functional features from the logical aspect. You can say that each opcode has a certain meaning and function, so it can be used as features. We expect that opcode features can also be successfully applied to smart contract classifications. But how can we get these opcodes? As we know, to enable the implementation of blockchain applications, Ethereum integrates an Ethereum virtual machine, EVM, to its platform. EVM is the runtime environment for EVM bytecode. Thus, the process of creating an Ethereum application can be divided into 3 steps: writing its source code in high-level language such as Solidity, compiling it into EVM bytecode, and eventually uploading it on the Ethereum blockchain. Once the contract has been uploaded, it is active. It can create and receive transactions, but most importantly, its bytecode is immutable. We can get contract bytecode easily on some public blockchain APIs, such as Google BigQuery. After we get the smart contract bytecode, we can use EVM-DIS, an open source disassembler, to convert contract bytecode into its equivalent in opcodes. Thus, opcode of each smart contract can be obtained, no matter it is open source or not. Then we can train our model or classify smart contracts only through opcode, rather than source code. The overall framework is illustrated as a figure. We first collected and verified smart contracts by crawling from Ethereum Explorer, such as etherscan.io and stateofthedapps.com, including the contract bytecode and related account information. The 6th step converts the bytecode into opcodes and extracts the code features to train the zero-day model, which is able to classify contracts once they are uploaded. The 3rd step integrates the contract behavior features from the transaction history to train the full feature model. Full extraction and selection and feature extraction are the key upstream capabilities for building a high-performance classifier. In our work, we built a zero-day model that is based on code features to classify contracts as early as day 0. This is possible because the code features are available immediately and are immutable once the contracts are uploaded. For code features, as we said before, we can use bytecode assembler to change bytecode into its equivalent opcodes. Then the frequency of each opcode in the contract will be counted and stored in the database. We merged and the frequencies of some opcodes in the same categories into one, such as DAP1 and DAP2 into one DAP12 feature. Account features are selected from account attributes and the related transaction history information. These features are only available after the deployment of contracts and may change over time, reflecting how contracts work in a real environment. Thus, we can extract these features from already deployed contracts. We selected several significant account features, such as balance, the number of investments, and number of payments. Once we have these 2 kinds of features, we integrate code features and account features to train the full feature model to improve the classification accuracy for the existing contracts. We choose in simple learning to train our classifier. In simple learning is a machine learning method that uses a specific rule to combine multiple classifiers as a collection to achieve better predictive performance than an individual classifier. The idea of in simple learning is that even if a weak classifier obtains an incorrect prediction, other classifiers can correct it. Bytecode-M1 is a typical simple learning algorithm that has been widely used to solve multi-classification problems because of its good performance, low complexity, and a good resistance to overfitting. Bytecode-M1 creates a simple weak learner from each feature, and weak learners do not in high accuracy in the initial stages, as long as the accuracy is higher than random classification. The weight of the correctly classified samples decreases, and the weight of the incorrectly classified samples remains unchanged after each iteration. So the classification accuracy of the overall model will gradually improve. Also, we choose C4.5 as the algorithm of the weak learner based on two reasons. First, there are many missing values in our code features. Thus, C4.5 is suitable for our cases as it has good performance and it is not sensitive to missing values. Second, although all of the binary classification algorithms can be expanded to multi-classification versions by the one versus one or one versus all strategy, this significantly increases the complexity of the algorithm. So we choose C.5, let's say 4.5, which can be directly used in multi-classification programs. Experiments were conducted on 11,000 smart contracts we collected from internet. Table 1 and Table 2 show the performance of each algorithm on the zero-day model and the full-feature model respectively over our dataset. The results show that the gap between the two models are tiny. In fact, 23 code features and only 2 account features were selected in the best feature subset of full-feature model. It means that account features have little impact on classification performance. That is reasonable because account features are not stable since they change over time and can be influenced by many external factors. For example, market and policy changes may lead to a substantial increase or decrease in transaction data. Thus, account features are not robust enough to be as key features. In most cases, our zero-day model is sufficient for both newly uploaded and deployed contracts because contract bytecode is immutable after uploading. Table 3 shows the performance of our approach and a representative state-of-the-art NLP-based approach, the SCC by LSTM algorithm. For verified open source contracts, the SCC algorithm has a slightly better performance than our algorithm, but the results are very close. For unverified contracts, our algorithm remains at high performance. In contrast, the SCC algorithm becomes a random classifier due to a lack of code features. These results indicate that our bytecode-based approach has similar performance with state-of-the-art NLP-based approach and is able to classify smart contracts even the contracts are not open source. So that's all. Thank you for listening.